All right, so today we're going to be taking a look at stretching, reflecting, and translating parabolas. So rather than going through the actual lessons that I've already posted for you, I'm going to kind of do a little bit of a demo using Desmos files that are shared with you in Google Classroom. So we're going to be taking a look at it. So as you can see, the title here says stretching and reflecting quadratic relations, which essentially means not so much the quadratic relations. You're going to be looking at the algebra and the graphs themselves. So you can see I got a Desmos file already set up. So rather than walking through the completed lesson that you'll be able to find in your Google Classroom access on your Google Drive, I'm going to just talk about using Desmos, all the key language and the key information, and then hopefully the information that's on the lesson itself will make sense. So the key thing for this idea of stretching, reflecting, and even translating is being able to compare it to what we call a parent graph or base graph or original graph. It really depends on the textbook, the teacher, whoever really you're talking to, but you got to compare something. So, think of it as an elastic band. If you have it sitting on a desk, it looks a certain way, a certain shape, but then you can pick it up and you can stretch it and twist it. So in comparing it to what it used to be, it'll be either longer or shorter or whatever. So there has to be some sort of comparison. So what do we talk about in math when it comes to quadratics? Well, we compare the base graph, what we call parent relation y equals x squared, to everything else. And then we make a comparison to see what happens. All right, so there's some terminology that you'll see, but I think it's probably easier if we just go through the Desmos file to explain exactly what's going on in terms of how this works. So what you see on the screen right now is the parent graph, as I'm going to be referring to it as. So you'll notice there's a couple of colors here. So don't worry about that too much because I can always turn one off, turn it off. So right now they're exactly the same. Now, why are these two graphs exactly the same, even though there's the letter A here? Well, because I have the A value as 1. So as you know from the algebra, the A value is your lead coefficient, as we've sometimes referred to it as. And if the A value is 1, then that really means 1 times your x squared values. So if your x squared value is 4, 1 times 4 is 4. And if your x squared value is 1, 1 times 1 is 1, and so on. So these are some key points on your parent parabola, and I've labeled them two different ways here because one of them is going to move. So the key thing is making a comparison. So we've kind of looked at this already, but we're going to look at it more in depth. So the first idea is stretching and reflecting. So the idea about stretching and reflecting is taking a look at not so much the x values. You'll notice this one key point here. It's going to be the y values I want you to focus on. Okay, so the y value is what I want you to kind of key in on in terms of what's happening here. So focus on the y values and comparing those two to see exactly what's happening. All right, so as I change this a value from a1 to something bigger than 1, so there's 1, all of a sudden this goes from 1 to 1.1. So now these points start separating, not that much, but very little. So this one blue one here is going to be fixed on your parent graph, and the other one is going to change. So you notice the table's already changed in values. And again, you're taking the a value, multiplying it by these current values. So 1.1 times 4, 1.1 times 1, and so on. So it's a multiplication. So what's happening though is you're multiplying the previous y values. So let's just put that back. So these are the y values I wanted you to focus on. So you're taking a look at changing the y values. And if you look at the graph as the y values continue to get higher on the black graph, talk about why this is referred to as a stretch. So you notice I've got these things here, these green dotted lines that kind of maybe look like, elastic bands, chains, whatever you'd like. But key thing is in comparing it from this original point down here and here, the new points have been stretched up. Now, why are they stretched up? Because the y value has changed. Okay, so that's very important. It's the y value here that has changed, not the x. You notice the x value is exactly the same. And the reason why that's happening, take a look at the a value. So the a value is what's affecting those y coordinates. And again, the reason for changing the y values is these are the original y values. Because remember, the function, or sorry, the relation that you have is y equals x squared. So these are all y values, and they're being multiplied by your a value. And that's how you're getting these new results. Okay? And the language comes from the look of the graph. So the original graph is this blue one here, and the new graph is the black one. So in comparing the black one to the blue one, we say that it's been stretched vertically. So again, it's going, all the y values are moving upward and it's being stretched. Now you might be curious as to why this one hasn't moved. Well, if you think of the y value here, the y value is 0. So it doesn't matter what you multiply 0 by, you're still going to get a 0. So that remains as a fixed point, which has a special name. I'm not really going to talk about it too much, but don't worry about that too much. All right. So just the idea that this parabola has gone from the blue shape to the black shape, and we call that a vertical stretch by a factor of 3.7. So that means that all the y values on the blue graph have been multiplied by 3.7. If you notice, that's what I've highlighted over here, to get the black graph. So if that y value, if that a value were to change, so if we drop it down to 2.5, so now the black graph was created by stretching the blue one by a factor of 2.5. Okay? So that's essentially it in terms of the stretching. Now the compression, the reason why we talk about compression is it's basically the opposite in terms of the look of the graph anyway. So I'm going to slide this up a bit so you can see what's happening. So I'm going to put the a value back to 1 so that both of them match. So if I slightly decrease the a value, so now it's less than 1. So if you look at the black graph and compare it to the blue one, it's being pushed towards the x-axis. So you notice even those green dots pushing it towards the x-axis, pushing it towards the x-axis, pushing it towards the x-axis. We call that a compression. So think of compressing something when you push down on a spring, for example. It pushes everything in a downward direction. So again, the black graph is created by compressing the blue graph by a factor of 0.1. Okay, so it's all this language that you really have to get used to. So visually speaking, again, you always start off with the parent, and depending on what happens to that a value, if the a value gets less than 1, we say that the graph is being compressed. The parabola is being compressed vertically. If we go back to the 1, and then the a value suddenly changes higher than 1, then we say that the graph has been vertically stretched. Okay, so that's essentially the main differences between stretching and compression. Where it gets to be a teeny bit more complicated is if you also combine a reflection. So a reflection just essentially means exactly what I have there. So the black graph has been reflected along the x-axis. Now, why does that happen? Well, if you look off to the side here, what I've done is I've put in a value of -1 for the a value. So that will make it reflect, open down. We've talked about that before. We've talked about opening downwards before, so that should not be a surprise. Now, so that's essentially when the a value becomes -1. So we'll get it to -1. So there's -1. So you can now say the graph has been, the parent graph, y equals x squared, which is the blue one, has been reflected along the x-axis, and now we have the black graph. But in addition to that, So if I change this a value, now watch what happens to the a value off to the side here. So if I make the a value less than -1, and just for reference, I'll put in, there's the reflected graph. So if I start making that a value larger or less than -1, so a bigger negative, if you want to call it, notice it's stretching away from the x-axis in comparison to the blue dotted graph. So the blue dotted graph is the reflection. The black is stretched away from that blue dotted graph. So again, there is a stretch in comparison to the parent graph, y equals x squared, but it's also a reflection. So there's two things that are going on. So a reflection because of the a value being negative, and a stretch because the a value is actually less than -1. Okay, and it works the same way with compressions. So we can get it back to -1. So now we have, whoops, sorry, get it back to -1. Actually, it's probably easier just to type it. There we go. Okay, get it back to -1. So now we have a reflection in comparison to the parent graph. And then we're going to make this a value still keep it negative, but now it's between 0 and 1. So take a look now. The black graph is being compressed towards the x-axis. Okay, so it's still reflected because it's opening downward, but it's now compressed. So it's two things. So again, we're comparing it to the original graph, this one up here, the parent graph. So if we compare the blue graph with the black graph. So first it got reflected, and then it got compressed. And if you take a look at the a value, the reflection is because of the negative, and the compression is because of the a value is between 0 and -1. Okay, so those are the main concepts in terms of trying to deal with this language of compression and stretches. All right, so again, quickly review. So get it back to your parent graph, a equals 1. So we have the parent graph. That would be a vertical stretch. Back to the parent graph. There's a vertical compression. And then we can talk about both a reflection in the x-axis, but not only a reflection, but a reflection and a stretch vertically. So again, we're always comparing to this parent graph, the blue one up at the top. So it's been reflected and stretched vertically, or it's been reflected and compressed vertically. Okay, so hopefully that gives you a decent basis for the aspect of the stretches and compressions. Just going to open up a translation file, so this one will be a little bit easier. So with the translations, so that lesson again, I'm not going to go through it formally. It talks about two letters, H and K, and talks about the different movements. All right, so, and again, I do ask you to try this with Desmos if you'd like, but it is important to get used to the algebra, and I will quickly go through that afterwards. But again, with the translations here, the key thing is, again, starting with this parent graph. Okay, so you have to have this comparison. So the vertex now is going to be the important part. So to translate this up is a fancy way of saying move it up. So if we want to move this vertex up, now again, focus on what aspects of the vertex are changing just for a translation up and down. So see which one of these values actually changes. So here's the algebra here off to the side. So I've got y equals kx squared, or sorry, y equals x squared plus k. That's the letter that's used. Doesn't have to be the letter k, it could be any letter, to be honest with you. Right now k is 0. So if k is 0, I really have y equals x squared plus nothing. So that's your parent graph. As the k value increases, no surprise, if we're going to add something to the y values, take a look at what's happening to the vertex. So we're adding to the y values. So the y value for the vertex and all the points on the graph start here. And then I'm going to take all those y values and move them up. So the key point is the vertex. So notice the vertex has gone from 0, 0 to 3, 3. It used to be down here at 0, 0. Now it's at 0, 3, and look at the k value. All right. So, and if the k value is negative, again, comparing it to the parent graph, it's now down here. So the language is like this. So we start with the parent. If we have a new graph, same shape, it's just been moved up. We call that a translation up or move up. And then similarly, start with the parent graph. And if it's the same shape and moves downward, we call that translating down or moving down. So you can also include or talk about translating to the left or to the right. So again, focus on the vertex here. This is the parent graph. Algebra looks a little bit different though. So now because we're moving left and right, we have to change the x coordinates. So the x coordinates are changed through this algebraic notation x minus h. Now, if h is 0, then that's x minus nothing squared, so we still have the parent graph. But as h becomes positive, oops, forgot to turn it on. There it is. H becomes positive. Now take a look at the vertex. So compare the vertex here. So this vertex was 0, 0. Now it's 1, 0. All right. Oops. And the reason why it's 1, 0 is because the h value is 1. So h value is 1. Vertex is now shifted over. And that's, so we can talk about translating to the right. We can talk about translating to the left. And it's all based on this algebraic expression x minus h for going left and right. Now that's a little sneaky with the algebra, and we will talk about that. And then you can combine them all, or these two different translations, the h and the k. So watch what happens here. So I'm going to take the h and the k, and I'm actually just going to hit the play button on the translate and zoom out. I have to turn that graph on. Oops. All right. So as you can see, it's translating up and down. Then I can also translate left and right. So now we got everything happening. So let's just make sure we get the right graph here. Okay, so we're gonna pause these. Don't really need those going. All right, so the graph that's moving around, actually I'm gonna change the color of it. Let's go black. There we go. So this one's just bouncing around based on the h value changing. Zoom that out. All right, so it's just moving back and forth. Now you might say, why is it down there? Well, because I have the set k value. So if I bounce the k value around now, so now this graph's going to be moving all over the place. So in comparison to the blue graph, it can move up, down, left, right, all over the place. All right. The key thing is, once I stop it, actually let's get a different value there. All right. So the key thing is, if you look at the algebra, x minus h all squared plus k. So that's the new form that you can be taking a look at. So you've seen factored form, standard form. This is called vertex form. Okay, so you notice the vertex is h comma k. Now, why is that the case? The old vertex was 0, 0. So if the k value made the graph move up and down, then that's the y coordinate. You notice the k value is -4, so the vertex is -4. And if the h value moved it left and right, now the h value is 5, and the y coordinate, or the x coordinate for the vertex is 5. So the graph has translated 5 to the right, and 4 down. 4 down, because the k value is negative, and the h value is positive 5. So positive 5 makes a move to the right for the h value, and negative 4 is going to make it move to downward direction for the k value. So again, the letters here for the vertex h and k. All right. So hopefully this gives you a little bit of demo in terms of how this works, and then I'm going to briefly go through the lessons quickly in a separate video.